Good morning. Thank you all very much for being here and for supporting all of the work that we do at the OPDC. As Professor Hu just said, my name is Tiago Griffiths. I'm a student psychologist, and I've been given the privilege of working on the Neuromotor Pen project. So the aim of this project was to turn simple pen and tablet tasks into numbers with the view to improve how we detect and monitor Parkinson's disease and related conditions. So a quick overview. I'll start with how movement is assessed in clinic, and then I'll introduce the digital assessments and the Neuromotor Pen, go through some of our results and the methods that we use to get them, and then finish with some conclusions and future directions from the research. So, some context. Motor examinations are the cornerstone of diagnosing and monitoring Parkinson's disease. The clinical examination is the gold standard, especially the MDS-UPDRS Part 3 motor score, which evaluates bradykinesia, the slowing of movement, as well as tremor and rigidity. We have other tools that add further information, like the timed up and go, rising from a chair, walking 3 meters and returning to the chair. The Purdue pegboard, where you place pegs inside a board in front of you as fast as you can, and the flamingo test, where you stand on one leg for as long as you can, or up to 30 seconds. So some strengths of these tests: they're standardized, they're globally recognized. They've been validated in diverse cohorts across the world, and they also capture a holistic view of Parkinson's, with motor and non-motor features being included. However, some subtle early signs can be harder to spot by eye. These assessments require specialists, they require patients to come into clinics, and they can be quite costly to perform. Also, they're only snapshots, so the results that we can get can vary between raters and also within participants, especially on and off periods. So our question was, can we track changes using an additional objective readout that's simple and convenient alongside the standard clinical exam? This is where the digital assessments prove useful. Digital assessments assess things like XY movement, pressure, time, speed, acceleration, and orientation, so that we can quantify movement accurately. Exploratory devices like the smartphone and wearables are already proving what's useful. You'll hear more about them in a presentation later. Some strengths of these digital assessments is that they provide objective readings that are sensitive to those subtle changes. They produce rich data from minimal tasks that can be performed remotely multiple times a day. And also they're scalable, with over 70% of the world now having access to the internet. However, the data is complex. It requires careful data analysis pipelines that need validation before use. Also, they're unsupervised, so if performed incorrectly, we might get invalid or false readings. And technology is now evolving so rapidly that it might be hard to keep up with the latest technologies and methods being used. However, the opportunity here is still great. And this is where the Neuromotor Pen comes in. So the Neuromotor Pen is a simple pen and tablet design that uses gyroscopes and accelerometers to record precise position and time as you draw and write. It's intuitive, it's non-invasive, and it's rich in data. We can measure 2 upper motor limb symptoms, which are bradykinesia, again that slowing of movement, and kinetic tremor. This is the tremor that is caused through voluntary movement. We can measure the tremor's frequency, the speed of the tremor, as well as the amplitude, the size of the tremor. So some earlier reports, mainly linked to teams that founded the device, suggested some differences between Parkinson's patients and healthy controls, as well as some medication responsiveness. For example, movement time significantly increasing on medication, but writing size not significantly changing. Our role was to step in and externally validate these findings, and also to introduce that prodromal group of idiopathic REM sleep behavior disorder participants who have a high likelihood of converting to Parkinson's in the future. So our aim was to evaluate the NMP as a digital motor tool, with our primary objectives being to replicate the PD control differences and to test these with the clinical motor scores from our clinics. Secondarily, we wanted to include that prodromal group of IRBD participants and to add in machine learning to see whether this adds classification value. So what did we do? We recruited 78 participants between 2022 and 2024. 36 of these had Parkinson's, 22 IRBD, and 20 controls. Each of these participants completed 5 writing and drawing tasks with each hand that took approximately 20 to 45 minutes in total. All of the participants also completed our traditional assessments like the UPDRS-3 and the Purdue Pegboard, allowing us to directly compare the digital with the clinical data. So I'd like to thank you all again for contributing to this research. We wouldn't have been able to do it without you. What did the participants do? So, there were 5 tasks, as I said, and the circle task involved tracing a circle 10 times as fast and as accurately as possible, the zigzag tracing a zigzag 10 times as fast and as accurately as possible, and the EL task writing EL, 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 EL 10 times in continuous cursive writing. Then the final 2 tasks were the FITS tasks, with a short and a long version, where participants tapped on the screen on 2 dots on either side of the screen, as fast and as accurately as possible for 20 seconds, with a long version, the dots being further apart, and the short version, the dots being closer together. So after we got this data, we pre-processed it by standardizing it and cleaning it, and then we extracted our features of bradykinesia movement time percentage change between each of the trials, as well as the movement time slope, which is the linear slope across all of the trials. We also got kinetic tremor frequency and amplitude. Then we used Pearson's R correlation to correlate these findings with our standard clinical motor scores, which were the UPDRS Part 3, bradykinesia and kinetic tremor subscore, as well as the Purdue Pegboard. And then we introduced that machine learning to see if we could find any specific data that distinguishes the Parkinson's patients. Okay, so firstly, a confidence check. Our standard clinical measures performed exactly as we expected them to, with the UPDRS up top, higher scores relating to more Parkinsonian symptoms, and PD being highest, with control being the lowest. With the pegboard at the bottom, higher scores relating to better manual dexterity, and the controls being the best, with the PD being the lowest. Unfortunately, we didn't find the same with the kinetic tremor frequency up top and the amplitude at the bottom. There was no significant differences from an ANOVA statistical test, with the means all being roughly in the same area. Furthermore, with the bradykinesia test, with the movement time slope at the top and the movement time percentage change at the bottom, the means were all roughly in the same area, with no significant differences being detected by any of the groups. Now, when we ran the correlations, we had tremor frequency on the x-axis and the kinetic tremor subsection of the UPDRS on the y-axis. There was no significant correlations between any of the groups here. But this is unsurprising, as kinetic tremor is not characteristic of Parkinson's and is usually a rest tremor. So the fact that the circle didn't pick up a kinetic tremor wasn't surprising to us. However, when we ran the bradykinesia correlation with the movement time slope at the bottom and the bradykinesia subsection on the left, we did find a significant correlation for the control group in blue down here. So it shows us that there is some valid measure of bradykinesia being picked up here. There was no significant correlation for the red PD group or the green RBD group, but you might notice that the control group has much lower variability, with the dots being closer together than both of these groups. And this could be because we didn't factor in factors such as disease duration, affected site, or on-off state. So when we factor these in the future, we could expect to see much stronger correlations between the bradykinesia measures from the Neuromotor Pen and the subsections. Machine learning. So we used sophisticated algorithms to classify the data, and the classification performed quite well when we used the clinical and the digital data. The digital-only data was weaker, however we only used one task, and so there was much less features to go into it. So when we analyze all of the tasks and add features, we expect the classification accuracy to improve. So in summary, there are some promising findings even though they're preliminary. The Neuromotor Pen is showing us some insights into tremor and bradykinesia that are meaningful. Our further analysis will include all of the Neuromotor Pen tasks. We'll also factor in disease duration, on-off state, dominance and affected side, and we're also going to try and correlate it to the smartphone app that you'll hear more about later. Okay, thank you all very much for listening. I really appreciate it.